Hello, Graph Data Science people. My name is Zach Blumenfeld. I am a Graph Data Science product specialist here at Neo4j, and today I'm going to talk about some of the highlights from our latest release, Graph Data Science 2.3. First, if you are absolutely new to Neo4j and new to Graph Data Science, I'm going to put some links in the description. There may be some videos you can watch before this to help you get a better idea of the product and what it does. Nevertheless, I am going to do a short recap here, just very briefly to get us caught up. After that, I'll jump into some of the specific highlights that we have for the product. So to get us started, what is Graph Data Science? Well, conceptually, Graph Data Science is basically just using relationships between data points for analytics and machine learning. And I know that sounds very general, and it's meant to be general. It's the idea that you can take things from machine learning, from visualization, from querying and search, and you can combine them to be able to analyze graphs for creating insights and for a whole host of other tasks. And this includes things like graph neural networks, which you may have heard about, but also a ton of other stuff, like being able to find efficient paths or find optimal subgraphs for different business problems, being able to find things that are important inside of a graph, being able to understand what might happen next, how the graph might change over time. All of these things go under this concept of graph data science. And so when it comes to Neo4j, you may know Neo4j as a graph database. Neo4j started out as a database company, and we have a very great database that does a lot of wonderful things. But Neo4j is no longer just a database, it's also an entire graph data platform. And the data science part of that platform is being able to take data from the database and also from external sources and creating something called a graph projection. And having these graph projections live inside of an optimized workspace, basically a workspace that's massively parallelizable, where you can run different graph algorithms and different computations very efficiently. So this is things like running centrality, pathfinding, community detection, similarity. These are all different types of graph algorithms that can provide insights and value. Engineering features from the structure of the graph, building entire pipelines, native ML pipelines for doing things like classification and regression and predicting links or relationships between different entities, and also integrating with other external machine learning frameworks. So we have a Python client, you can move data really efficiently in and out of that environment, integrate graph features inside of more general purpose machine learning frameworks, and all that sort of good stuff. And now that we've gone over that very brief overview of graph data science at Neo4j, I'm going to jump into some of the highlights for this most recent release, Graph Data Science 2.3. I'm going to split this up by 4 of our key investment areas, the first of which is making better predictions. And this is probably where we're going to spend a pretty significant portion of our time. Now, there's no way I'm going to be able to go over every single thing in this release that's changed or improved. There's just too much for that. I'll go ahead and put a couple links in the description, which will go over all of the various changes in full detail. For here, I just want to go over some of the bigger ticket items. So in making better predictions, we're going to go over a new pathfinding algorithm for Steiner trees. We're going to go over a new type of graph embedding. And we're going to talk a little bit about some improvements to the native machine learning pipelines for handling class imbalance. So to start out for pathfinding, we've included this new algorithm called minimum directed Steiner tree. And basically, what it does more or less is find optimal subnetworks within a graph. And specifically, it finds a tree that can connect a subset of nodes in the graph together using the lowest cost measured by weights on the relationships. And this is a really valuable thing to have for optimizing difficult routing and supply chain problems, for example, figuring out how to do infrastructure planning, and a whole host of other things that are variants of what we call the traveling salesman problem, basically trying to find points that are connected together in a way that's going to be the most optimal. Here's an example of me using the minimum directed Steiner tree algorithm in Graph Data Science to solve a freight forwarding problem. Basically, I have this data set where I have freight coming from multiple locations, and going on airplanes through various business segments and various flight segments and all of these processes, and they need to be combined and set to a common location. So I could have 2 to 3 to just a single source airport, and I need to get it all to a destination airport, and there's multiple hops in between. The data set has a few thousand of these shipment inferences. I've gone ahead and loaded all the data in already. And you can see that I can basically just make a graph projection from what's inside my database. I could set the different entry points or source airports and the target airports. And then I can write a solution to the graph, an optimized solution. You see there, that cost is the total cost, the sum of basically all of the time across the business process. And it figured out in this really messy problem how to combine all the different potential paths together to figure out the most optimal combination. And here you can see the solution in our workspace application. You can see that it found this tree among all of the hundreds of thousands of different potential options that optimizes the cost and actually put all these different stops in between to combine different cargo together. Now let's talk about HashGNN, our new node embedding algorithm, which we're going to be calling our Knowledge Graph Embedding. To understand HashGNN, it's going to be helpful first to go over what a node embedding is. A node embedding is basically a way to represent every node in a graph with a low-dimensional vector, such that nodes that are similar in the graph, being in the same community or having similar attributes, are also similar in their vector space. And we can essentially use these vectors for downstream processes, whether it be exploratory data analysis, similarity measurements, or as features for machine learning. And they help save us time and reduce work by generating features in an automated way rather than having to manually generate features from relationships. And by encoding relationship information inside of these vectors, they can increase their performance and the insights that we get in these downstream machine learning processes. Now, we already have quite a few different node embedding algorithms, from FastRP to GraphSage and Node2Vec. This new HashGNN algorithm that we're adding has a couple of unique things associated to it. Here is the archive.org version of the paper where HashGNN was originally conceived. Link in the description. A big motivation behind HashGNN is the fact that GNNs, or graph neural networks, do exist for creating embeddings. However, they can be very slow because they require training a relatively complicated model and require doing many complex traversal and aggregation procedures. So what HashGNN does is it mirrors a graph neural network architecture, but instead of training a model, it uses a clever application of hashing functions and essentially creates a vector representation for each node in binary format. And the more similar those binary formatted vectors are, the more similar the nodes are in the graph. So essentially, it functions similarly to a graph neural network, but it's faster. And in benchmarks within this paper, and also some of our own benchmarks, I'll go over an example in a bit, we find that it performs in a comparable way to state-of-the-art GNNs, which is really exciting. Now, our implementation for Neo4j extends on the original paper a bit. Like I said, the original paper looks at binary input for binary output for the vectors. It uses message patching like a GNN, but uses those hashing techniques to speed things up. Inside of the Neo4j implementation, we do something similar. However, we have also allowed the ability to encode graph heterogeneity, which basically means that it could account for and adjust for different relationship types in the graph. So it can take in a little bit more information. It can be used with or without initial node property input. So if you just have a graph without any properties for the nodes, you can still run it. And it can do a few other things, like it can use numeric input, not just binary input, and create numeric output, not just binary output, which might be helpful for working with different machine learning models downstream or using different types of node attributes to begin with. Here's an example of using HashGNN, also in conjunction with our native node classification machine learning pipeline. Link to this notebook will also be in the description, like the others. What you'll see here is us using the Graph Data Science client. Here is just starting it up, getting connected. We're going to be loading the IMDb dataset. Basically, this dataset is a graph of movies connected to actors that have acted in the movies and directors that have directed the movies. And the task for us will be predicting the genre of the movie. You'll see here that we have some movies which have a genre, other movies that do not have a genre. We labeled them as unclassified movie. And each of the nodes also has this plot keywords parameter, which is basically a 0-1 indicator for different words that show up in the plot of the movie or in the aggregation for the actors and the directors. We set up a pipeline here using our Python client. This is just configuring a pipeline. A lot of this is stuff that you might be familiar with, sort of an ordinary machine learning workflow, creating a pipeline, configuring test and train splits here. This is where we add HashGNN into our machine learning pipeline. And there's a lot of hyperparameters here. I'm not going to go over all of them. Important things, we're setting the embedding density, which is more or less the size of the vector or the size of the node embedding, to 512. We're using those plot keywords as properties to input into the algorithm. We're also setting heterogeneous equal to true, which means that it's going to use a different set of hashing functions for different relationship types. We're going to go ahead and just select that feature that we make inside of the pipeline. We're going to add a logistic regression model candidate as well as a random forest model candidate, which we're going to compare, and whichever model does better, we will select as the final model. There's also some ranges here for hyperparameter tuning. I don't have time to go into all of that. If you'd like, you can pick up this notebook afterward and look at our documentation for how that works. This is where we actually train the pipeline on the graph projection. We are going to focus on an F1 metric as the final metric. Once that's trained, we can see our F1 score, and we can understand a little bit about the winning model. There's some things here we can do. For example, predict mutate is essentially just predicting on those unknown movies using that model that we just trained. The model is persisted inside of Neo4j. And it can be used to predict either on the graph projection or back to the database. The interesting conclusion that we have here from this graph transformer paper linked in the notebook, this was done with a variety of different graph neural network algorithms or graph neural network models. We see them listed here, and for this test, this is where they get their F1 score. So you can see some names that might be familiar if you're familiar with graph neural networks: deep walk, graph convolutional neural networks, graph attention networks, and graph transformer. And our F1 score, around 59-ish, is very close to the top performing one, the graph transformer network. I would argue almost within the margin of error. And this is impressive because we are able to do this with HashGNN, which doesn't require model training, doesn't require a GPU, and can complete very quickly. And we can get very good performance off of it for this node classification problem. Obviously, you could also use this HashGNN by itself, not just in a node classification pipeline. And you can export those results to integrate with whatever other machine learning framework you wanted to. Now, the last thing I want to mention under making better predictions are the new configurations we've added for handling class imbalance in our native machine learning pipelines. So there's a few different things that we've done for this. The two that I'd like to mention are introducing class weights and introducing focal weight as a parameter for node classification and link prediction problems, specifically for logistic regression and MLP, which are just the two model candidates for these types of problems that we've selected for this new feature. And class weights is basically just a vector of class weights. So whether you have a binary classification problem or a classification with 3 or more different potential target classes, you can have a class weight vector to weight the different classes respectively based on the imbalance. The other one, focal weight, is a little bit more unique. Basically, it's setting a single non-negative value to reflect something called the focal loss factor. And all that really does is it changes the loss function. So the default would be 0, which would basically be doing nothing. And then as that number goes up, you can see here in this chart on the right-hand side that you get more dispersion for misclassified examples. So it's a little bit more general, and it can help essentially provide more weight to really troublesome examples that are misclassified in your data. So these types of things are useful, again, for really strongly imbalanced problems. So things like fraud detection, certain types of entity resolution, recommendation to a certain extent can benefit from having these configuration parameters. Moving on to our next 3 investment areas, I want to talk about production readiness. Again, there's a few different things under here. For sake of just talking about the highlights, I want to go over the performance improvements that we've seen for some of our algorithms. Algorithm speed and scalability are very important for us because our environment is optimized specifically for graph. We can parallelize and scale a number of different things. This slide just shows some of the algorithms that we have on some pretty decent sized graphs. You can see things in here like FastRP, which is a type of embedding running on a graph with 2 billion relationships and the timing around that, as well as things like weakly connected components, which is a type of community detection. It helps you understand how to partition your graph, and things like label propagation as well as another type of community detection. And on LDBC, we also have benchmarks around doing things like k-nearest neighbor between nodes, node similarity, and node to vec embeddings. This slide is a little bit old. I think we are actually doing better than this on a few different algorithms right now. But there's a couple that I wanted to call out specifically for our GDS 2.3 release. And under these performance improvements include a community detection algorithm we call Leiden, which got 2 times faster. This is a very scalable algorithm. It works similar to Louvain, but it runs under concurrency quite well, and it's quite a bit faster. That's all a 2x improvement. A-star shortest path and Dijkstra single source and source target are all pathfinding algorithms. They help you find the shortest path between a given set of nodes. And these saw pretty significant performance improvements inside of our 2.3 release. And lastly, weighted betweenness centrality, which is a way of measuring how important a node is, how well it bridges across a graph, also saw 4x improvements. Moving on yet again to our next pillar under ecosystem integration and also being built for data scientists. We'll take 2 on for this last section since they're closely related. We've gone ahead and added some things that make it more convenient for moving data into the graph. We've, for a while now, had the ability to take external data either in a table or a data frame and map it over into a graph projection directly, which is very helpful if you're working, for example, in a Pythonic environment, or when you're trying to move data from another data store into Neo4j to do analytics. We've added some methods to make it easier for you to project what's called an undirected graph or undirected relationship types within a graph. You can see here that I can select different types of relationships that are in a tabular form and map them over to graph in an undirected form. We've automated that so that essentially you don't have to duplicate data in this process. And having these undirected relationships is very important for when you want to run certain types of algorithms, particularly things like embeddings and other forms of similarity metrics. You can do this with something called cipher aggregation. If you have the enterprise edition of Graph Data Science, or if you're using Aura DS, which has enterprise under the hood, you will also be able to leverage our Apache Arrow support for importing graphs, which can scale things up and make them very, very fast. So we can move objects very quickly into the graph, millions of relationships, millions of nodes within a matter of seconds. And in addition to that undirected theme, we've created methods that allow you to take graphs and map existing graph projections to undirected relationship orientations by relationship type, which again is just a convenience to help you conduct graph analytics. Now, we've seen in the demos that I've showed already that we have a Python client or a Python surface for working with graph data science, basically allowing you to run graph data science just like any other Python library, integrate with your other machine learning tools. It makes it easier to get started. We've added a few things to help improve this client. You've actually seen glimpses of them in the demos that I ran before, but basically this undirected relationship management is a configuration for when you're constructing a graph through the Python client. So you can see here I have this line that says GDS alpha graph construct. And what that is doing is it's taking a data frame of nodes and relationships and it's mapping it into a graph projection. You see that the number of nodes is the same at the end, but the relationship count has doubled, which is what I wanted. In this example, I'm actually projecting a graph, creating embeddings, in this case a different type of embedding than HashGNN called FastRP, and also with GraphSage. And I'm mapping these back out and using them to show how you can increase the accuracy of document classification by leveraging relationships in a citation network. So if you're interested in that sort of thing, how graph features can improve model accuracy over just using ordinary NLP features, we'll go ahead and put a link to this notebook in the description as well, and you can check it out. The last thing I want to mention about our Python client is our ability to load prepared example graphs. So you actually saw this with the IMDb dataset that I loaded earlier when I had my notebook on HashGNN. There's two other datasets that we have, Quora and Zachary's Karate Club. Quora is a citation network of scientific publications. Zachary's Karate Club is a very small social network that mirrors a university karate club. We've basically pre-canned these data sets, so these examples are ready to go, and you can load them with just one line of code through the Python client. And that allows you to get up and running very quickly with experimentation and testing out the platform. If you want to check graph data science out for yourself and get hands-on with the product, there are a few different options for getting started. First, for free, you can go to neo4jsandbox.com and set up a graph data science project. This is completely for free. All the infrastructure is set up for you, and there is a browser guide that lets you get started and rolling with examples right away. Another thing you might consider is downloading graph data science along with Neo4j and working with it either on your desktop, on a server, or inside of a Dockerized environment. You can go over here to the Graph Data Science manual to find directions for how to do that. And third, and something that I highly recommend, is using AuraDS. AuraDS is our software as a service cloud offering. Right now, this is set up in Google Cloud. And it does cost money to spin up instances, but if you're a new Google Cloud user, you can apply credits. You get $300 automatically when you set up an account in most cases. And being able to use AuraDS allows you to scale instances to a much larger size. So you can see here where you can go to an 8 GB instance to start of memory, but you can go up to 32, 64, and even all the way up to 96. So you can really get a sense of scale a lot better inside of AuraDS than with some of these other options. And that is a wrap for today. So in the description, you should find links to a lot of the stuff we were just talking about. We'll also put in links for the blog announcement for our 2.3 release. We'll put something in there for a what's new summary, be a written form of a lot of what I just said, goes into a little bit more detail. And we'll also include links to documentation and GitHub and stuff like that. So thank you for tuning in, and I hope you have a great rest of your day.